All right, I think we're ready. We're going to start on exam 2 content now. We've got, so we didn't meet, was it last Thursday? Last week sometime. Oh, I guess it was last Wednesday. Thursday was the exam. So there is a bit, let's see, right here, class 11, the one that's labeled class 11 anyway. There's a little intro. It says part 2 actually on it. I have to check that because it should be part 1. Maybe I'm need to put part 1 in a different place. Where did part 1 go? Is it on this one? No, that's beams. I'll have to look and see where part 1 of the frames went. They kind of seem. I'll re-link that thing because apparently part 2 is listed here, but part 1's not. So I'll change that to list part 1. But there is, we'll basically start from the beginning today, but if you want a little more thorough beginning to frames and machines, then I'll link that one just so that you can have a little bit more to it, although we'll basically do most of it today anyway. So it looks like there's some issue there with that not showing part 1 instead of part 2. Or showing part 2 instead of part 1. But the content from here to, where's the exam 2? There's exam 2. I don't know that this date is exactly right. I haven't gone in. That's the date from last year. So July 22nd, it's around the 22nd. I'll need to get the exact count up and see when that actually lands. We don't meet on Monday of this next week because that'll be the 4th of July holiday. But other than that, I'll be able to go in and figure out what date that is. But from now until then is all exam 2 content. So exam 2 is mostly about flexing. So exam 1, things were stretching or maybe compressing. We didn't really talk a whole lot about compressing because compressing means getting shorter. That has a little bit, it's on quiz number 2, class 9 is where, okay, why did it get way up there? Let me just fix that real quick. Thanks for, there's, it's called intro. Let me move that guy because that's not where that needs to be. Let's just do that real quick. So we'll just copy that. And let's put that on that class 11 where it should have been. We'll put them both back to back, so that'll be fine. That way you can see both of them together if you want them to be together. There we go. We got Frames and Machines intro, part 2. So like I was saying, the first third of the quarter is stretching, axial force. And things are stretching, maybe compressing. We do have to think about when things compress, a lot of times they're going to do what's called buckling. And so we kind of avoided that because it's this mixture of flexing and compressing. So we didn't really talk about buckling much. And so we really talked about things stretching, or if they compressed, then they just got shorter. They didn't try to buckle. This middle third that we're in right now is things are flexing. So they're bending. Let's see if I can find something that'll flex over here. Everything, well, this will kind of flex. So now they're flexing, like this. And then the last third is going to be all the things that kind of don't fit somewhere, plus twisting. So things will twist like that. So this middle third it's pretty interesting. We're going to take the same ideas where things are going to have a yield strength. If they flex too much, then they've permanently flexed, bent. And they have an ultimate strength still, so they flex that much, then they've fractured somehow. We're keeping it separate from the axial stress, though. So we're kind of keeping that part separate. And we're talking about these frames and machines. So they look like trusses sometimes. You can kind of see a picture of, there's a piece of one there. There's a little pieces of one there. It's important to be able to tell the difference in frames and machines and trusses. Because when we did trusses, then we had this idea that every piece, every member in the truss was what was called a two-force member. So they all had two forces on them, and they could be modeled by an axial force along the length of that member. And that's not true in a frame in the machine. It can have those pieces, but not every piece is going to be that way. And so this goes back to the what do we call them? The little assumptions when we talked about trusses, the beginning. We said that all the trusses were pinned at two locations. You know, they had two pins, one on each end. Did not have forces applied to the member. The forces were only applied at the joints and so forth. So all of those assumptions, a frame and machine is going to have at least one piece that violates at least one of those assumptions. And it's usually going to be that, one of two. It's usually either going to be that there's a force applied directly to the bar, you know, the little member piece, and it's not at a joint. So that's going to be one thing that'll say that you're working with a frame or a machine. The other thing is that maybe you've got, in fact, there's this little piece right here, this one right here, this diagonal one. It's got one pin, two pins, and then it's got a third pin that's got this pulley on it. So it has more than two pins. That'll be another thing that'll tell you that this is not a truss. Because once you find that it's a frame or a machine, then you know you can't use method of joints or method of sections. You have to use a process that's going to work with the frames or machines. I keep saying frames and machines because there's a little bit of difference in the two, but we're pretty much going to treat them exactly the same. The difference is that frames are stationary. You know, they look like trusses. They hold in place, but they have something that violates one of the truss assumptions. And a machine has parts where it can move, you know, relative to one another. So it's got slots or sliders or something where it can move around. As far as the way we're going to solve them, though, they're pretty much the same. Hey, let's see what our little poll. I put a poll in the chat. I don't know how to look at. Oh, there they go. If I click on it. Got only like 3 people counted on it. So that it's not much of a scientific poll yet with only 3 samples. Speaking of exam 1, the poll is about exam 1. Exam 1's been graded in Moodle, but I haven't gone through, so I'm certain there's going to be questions like you had to fill in the blank, right? Type in, fill in the blanks on some of them. There's certainly going to be some of those that I need to go in and check the spelling, because Moodle is not going to do well at, you know, you spelled a wrong word a little bit wrong. It's not going to do, it's going to mark it wrong. So I need to go in and do that. There's probably, I know I've had a couple of people email that they just marked the wrong thing down, but if I look at their work that they uploaded, it'll show, you know, the correct answer. So it'll be a little bit longer before I go through and correct all of the little things. I don't know of any instance where I'll make a correction and your grade goes down. Like, I don't know that that's going to happen. I don't remember it ever happening before. So I would assume that whatever's in Moodle is the minimum grade you're going to have on exam 1. There was also some questions about the retake. Some people looked ahead here or read the syllabus. Maybe it's not even in the syllabus. I don't know. But here, right here, August 11th. And again, that date is probably last year's date, so it's probably like the 12th. But exam 1 or 2 redo, what that is if you, for any reason, want to retake exam 1 or exam 2, maybe you missed it and you need to retake it, or maybe you didn't do very well on exam 1 and you think you could do better by the end of the quarter, then that date is for anybody. It's not just makeup exams. It's anybody that wants to retake exam 1 or exam 2. It's not exam 3, but 1 or 2. You can go in and retake the exam. It's not going to be the exact same exam. It'll have the same types of questions, but it'll have different actual numbers, different question types, but the same content. So it'll be equivalent to the exam 1 or 2 that you did take, but it won't be like an exact copy of it. So that is what August 11th, again, is probably not the actual 11th, but that's what that is anybody that wants to can retake one of those and replace the new grade. Typically, people do retake it, do about 1 question better, you know, so they make 5 points higher. Some people who had an issue, maybe, you know, they were sick when they took exam 1 or whatever, you can make significant improvements, but the average is about 5 points higher or whatever when you do the retake. Most people do retake exam 1, although it's your choice. You can do 1 or 2. Can't do both. And it just completely replaces your old grade. So the old grade gets erased and the new grade gets put in there, whatever it is. I have had a few, not many, but I've been teaching this like 20 years, so it's a lot of people. A few people do worse the second time. The few that have done worse have been like a point or 2 worse, so it was really no different. Basically, they didn't make any different grade. But if somehow you do worse, then that is your new grade. It's very rare, extremely rare, and I don't think it's ever happened where worse was actually a whole lot worse, other than a point or 2. So that's what that thing is. All right, let's head into these frames and machines. I just realized I never opened OneNote to write in, so I kind of need that. Let's get it open. There's a truss. We don't need trusses right now. Let's add a new page. I like for it to be green for some reason. I don't know why. There we go. All right. So I need to kind of reorient this. All right. So we're talking frames and machines. We'll put that in our little title up here if I can get the mouse over there. All right. So they can look a whole lot like trusses. Only they can have the same kind of structure and everything, but like I said, they're going to violate one of the rules for, or the assumptions, whatever you want to call them, for a truss. So what that will mean is that what ends up being the difference in these frames and machines versus a truss is that, trying to get this rotated, is that at least one member in a frame or a machine is not a two-force member. So at least one is not. There could be none that are two-force members, but at least one is not a two-force member. Let's just go back over two-force member too. So two-force member was here's a member. It has no forces applied to anywhere other than the joints. You know, there's no force. You know, no force right there. So only forces are applied at the joints. It is straight. It doesn't have to be straight technically, but this one is straight. And there are only 2 pins. So when we have that kind of setup, then that particular piece is a two-force member. And it meant that we could say that there's one force and another force over here, and they both happen to have the same magnitude but opposite directions because they balance each other out. They don't have to be in tension like I drew. They could be in compression. So that's the idea of what a two-force member is. But not everything is a two-force member. So it could be that you have to treat things this way. Now we need some letters. Well, this will be A and this will be B. And let's say this is not a two-force member. It's got a distributed load on the side of this piece for some reason. So definitely not a two-force member because there's a load directly on the side of it. Now when I get to A and B, instead of doing what I did before with drawing just F at some angle, remember that angle, you connect the dots between the pins for that member, and that determines the line of action for those forces, F. But that's not true when it's not a two-force member. Those are just pins now, and I have to treat them like any other pin, and I have BX and BY, and then at A I have, and I can put any direction I want, so I'm going to put them this way, AX and AY. And AX does not necessarily equal BX. BY does not necessarily equal AY. I've got this distributed load, we'll call it W. You have to treat this body, this member AB, as its own little free body, where you go in and you calculate summation of forces in X, summation of forces in Y, summation of moments about some point. So this one piece becomes a whole free body by itself, and that's useful because you have a bunch of equations you can use, but it does mean that you're going to have to deal with that. I lost the chat all of a sudden. There it goes. All right. You have to deal with them differently. And that means, so this is non-two-force member, I guess. So it's really convenient when you can look at a truss and find zero force members. It's also really convenient when you can look at a frame or a machine and find two force members. So basically you can go through kind of the same type of process before you start working on a frame or machine, where you're looking for these two force members. It's not the same set of rules as looking for zero force members. It's basically looking for any parts of the frame that behave like a truss. So you find a member, it only has two pins, there's no force acting on the member, only forces at the pins. We can ignore the weight of the member, all those things. If you can find one little piece of a frame or machine that behaves like a truss, then that one piece can be treated like a two-force member. Which is obviously, if just looking at these free body diagrams, it's way better to have a two-force member that you have to solve than this other thing on the other side where I've got, four unknowns and this distributed load and all this other kind of stuff. So it is convenient to be able to find them, but they don't necessarily exist. And you know for certain that not every piece is a two-force member when you're dealing with a frame or a machine. I think probably the best way to do the next part is to just grab some examples from WebWork. Let's see where to put WebWork. There's SolidWorks. There we go. I got this one. So this is in the optional. Now you have an optional 2 and a challenging 2, just like there was optional 1, challenging 1. There's a set for the second, third of the quarter. So this would be a frame. I can tell it's a frame because, well, I've got this member ABC. So it has 2 pins and then this connection over here at the wall. So it's certainly not pinned at the wall. And this is a new connection that we haven't looked at before, so we'll have to see how that works. And it's got 3 connections, 1, 2, 3 on that piece. This piece has 1, 2, 3, so it's got 2 pieces that are not two-force members. So this is a frame. I have to decide if it's a frame or a machine. It does have a pulley, but the way it's built, there's nothing that could actually move. It's just kind of hanging there. So it's just going to be a frame. All that the frame versus machine actually does is it kind of guides some of the very first parts of solving the problem. You don't even really have to be able to tell if it's a frame or a machine in order to start solving the problem. Just there could be a place once you start finding the external reactions that if it is a machine, a lot of times you have to skip that part and move, or they're already given or something. So there's no, other than naming them, there's not a thing that you're going to have to worry about knowing this is a frame versus a machine and I treat them differently. You treat them exactly the same. Let's see. We've got a lot to copy here. Let's copy this and then we'll look and see what it's asking for. So we need that all the way down. We can do without that part. Let's get that. And let's paste that guy right here. All right, so let's see what we have. The hoist pulley structure shown. So the hoist kind of makes you think it's a machine, but there's no parts that could actually move the way they've built it. is rigidly attached to the wall at C. So that's what they're talking about over here. The rigidly attached, maybe that keyword rigidly is a piece of it. We might call this a fixed support. I think that's the word that we'll use most often for naming something like this. Basically, what this is modeling is that this bar ABC is either like welded to the wall. In this case, it looks like it's embedded in the wall, or maybe it's bolted to the wall. You know, it's rigidly fixed to this wall somehow. Whereas with a pin or a roller, it has some degrees of freedom. So this is a new thing that we haven't had before. In fact, why don't we quickly go back over to what we've done. We've done pins where you've got something that, you know, it has two reactions, right? A pin, it can resist in the horizontal direction and the vertical direction. Doesn't matter which, you know, could be any angle and another angle that's perpendicular to that angle. So there's two reactions. We've dealt with rollers. And I would draw this roller on an incline just to make it different. And they're kind of like these little roller skates. Well, I put that roller on a pin. Hold up. That would be confusing. Let's just say that it can roll. And it's going to have one reaction, because it lets you move along the plane here, the inclined plane, but it doesn't let you move through the plane. Technically, I guess it could lift off of the plane, but we usually assume that it can't, like it's on some kind of track that it can't lift up. We don't get into that much worry. And these fixed supports, this is a new one. They're going to look different ways. A lot of times they're going to look like this one, though, where they're kind of embedded in a wall. They actually have three reactions. So not only does the beam being embedded in the wall mean it can't move left and right, and it can't move up and down, but also it can't rotate. So they actually get this kind of symbol. So this is a concentrated moment. So we haven't dealt with that before. So I've got the little beam and it's stuck in the wall. The fixture back here means it can't move left and right. It can't move up and down. And then the concentrated moment is saying it can't rotate either. Like a pin would let it rotate right here. But when it's fixed in there, it can't move up and down. It might can bend, but that's not the same. Flexing is not translating. Even though it might move around a little bit, it's not spinning around or anything. It's just bending. So that's a new one that we'll have to deal with in this problem. All right, let's see what else it says. It also says a load of sand, so that's the little triangle thing here, sits on a tray hanging from the cable. It passes around a 1 foot diameter, so this guy is 1 foot diameter. Frictionless pulley. So the frictionless part here means that I don't have to worry about the cable tension on one side of the pulley being different from the cable tension on the other side of the pulley. The weight of the sand can be treated as a triangular distributed load. So you can kind of see they overlaid a red set of arrows here that are unevenly distributed. So we can figure out how much the sand weighs with that. Maximum intensity of 70 pounds per foot. They are talking about this point right here, 70 pounds per foot at the peak of our little distributed load. And then it goes down to 0 pounds per foot at the edge. They don't have to go to 0 pounds per foot. This one does, though. So we get these little triangles that have a height of 70 pounds per foot and a base of C, or C over 2 if you're looking at two triangles. We've got all our other dimensions. Let's write those in. So A is 3 feet. B is, oh, wait, no. A is 2.5 feet. B is 4 feet. H is 3 feet. I think that's all of them. Determine all forces and moments acting on member ABC. That moment they're talking about is this concentrated moment that we just described when we described the fixed support. The shear stress on the cross section of the 1/2 inch diameter pin D, which is in double shear. So they're talking right here in the middle, that pin that holds the pulley into member ADE. It says it's in double shear. So what that means is, I don't know how it's arranged, but the pin, if this is, let's see, where can we put that? If this is the pin at D, then somehow it's going to break in 2 places. That's double shear. So it's going to have two circular cross sections that are in shear stress. And the double is referring to it has to shear in 2 places for it to actually come apart. All right, what else? The change in length of member BE. So member BE, this vertical piece, is going to have some kind of force in it that's probably trying to make it get shorter, compressing it. It gives us some dimensions for it and a modulus of elasticity, and we just have to figure out how much it changes in length. So that's a lot of stuff. So I think if we work through this one, maybe if there's some other questions come up, then we'll look at those. But I think if we look through this one, then we'll probably have done a pretty thorough job of at least introducing frames and machines. We can still work more of them. You do have, let me point that out while we have web work open. You do have homework. Oh, got logged out. Well, all the original homeworks are still open until the 30th, but you do have 8 and 9 now that are, no, 9 and 10. It's 9 and 10. 9 and 10 that we skipped over in the first third of the quarter. Those are relevant now. They're going to be the frames and machines stuff. So they're closing at basically the end of when exam 2 starts, more or less. So those have been open for a while, but they were new stuff, so I told you to skip over them. So those are your homework that relate to frames and machines. All right, we don't actually have a free body diagram here, so I'm gonna cheat. And did I ever get? I never did get a actual white color. It's kind of off-white, but I guess that's what I got. All right. So we will kind of just erase this, right? We really should redraw a whole free body diagram, but that's going to start taking a long time. So we're going to do it this way. I don't really need that circled. It just wants it to be circled, apparently. All right, good enough. So the cable over here, I'm just going to give it T. I don't even know if it asks for the tension in the cable. Yeah, it doesn't. So we're just going to give that T. We can find it right away, but I'm going to give it a variable T right now. Our fixed support is going to have, this was C, so I'm going to have a CX, a CY, and, well, we may have to figure out what to do with that. A moment at C. Yeah, maybe it'll kind of settle down. Looks like it's going to flip-flop back and forth all the time. I don't know. So we need to solve for CX, CY, the moment at C, T. Those are external reactions. So there's actually 4 of them. The trick, I guess if you want to call it a trick, the trick is that we actually know the tension in the cable. Wow, that's really annoying me that it's doing this. Let me try a different way here. Do I have a solid block? I may not. I think I can just, yeah, it just highlights it. Well, we'll deal with that. It's fine. So the tension in the cable, if you look at the cable, it just goes around this pulley and it comes over here and holds up this weight. And the problem statement said that this pulley was a frictionless pulley. So the frictionless part means that that cable tension is all the same no matter where it is. So if I just figure out how much this sand weighs, then that's how much tension is in the cable. So we can figure out T pretty easily. T equals, and again, we're ignoring the weight of the cable. We're ignoring the weight of the little platform the sand is sitting on. We're just going to say that the most important thing is the sand itself. So we have this little triangle that has a height of 70 and a base of C. I never wrote down C. I don't see it. A, B, H. Does it never? Let me go back to the original problem and see if we didn't get a value for C. This is optional 2, I think. I think it's problem number 2. Did I just totally miss it? The hoist. So tray hanging from it. Passes around 1 foot thing. Frictionless pulley at D. The weight of the sand is a triangular distributed load with a maximum and a width of 3 feet. Okay, so it's right there. It just doesn't say C equals 3. All right. So C is 3 feet. All right. So the tension or the weight of this sand, which is the tension in the cable, would equal. We just calculate the area of that triangle. So 70 pounds per foot, times 3 feet, but it is a triangle, so divided by 2. So 210 pounds equals T. So even though it looked like we had 4 unknowns, we actually did know the tension in the cable. Tension in the cable is 210 pounds. All right, now we need to figure out Cx and Cy. For those, and moment at C, we have our equations. Cy, maybe it would help to quickly draw the free body diagram since it's getting kind of junky there. Let's just draw it kind of simplified. What does it look like? Okay. And we've got that pulley there, and we've got the rope coming off, Tension in the rope is 210 pounds. This is 210 pounds, the weight of the sand. We have Cx, Cy, and the moment at C. We don't know what direction those are going, so I drew them all like positive, assuming that clockwise is positive on my moment at C. Now I can go in and, I don't know, summation of forces in the y direction equals 0. I've got Cy minus 210 pounds equals 0. The moments, concentrated moments, like MC, they don't have X or Y components. There's more like a point load that's, but it's a moment. It's not a X or Y direction. It is the idea that there's something that's wanting to make this beam rotate. And the moment at C is the thing that's keeping it from rotating. So the thing that makes it want to rotate is the fact that there's 210 pounds of sand hanging off of this thing, which unopposed would make the whole little frame here swing down. But it's opposed by this fixed support where the swing is stuck into the wall. The sand is wanting to pull it down. Moment at C keeps pulling it back up. So it doesn't have X or Y components though. It resists moments. So looking at this though, Cy must equal 210 pounds. And then we can do summation of forces in the x direction equals 0. And it looks like CX plus 210 pounds equals 0. So CX must equal negative 210 pounds. So what that means is that I drew the x component, this arrow, I drew it backwards. So CX is really supposed to be pushing to the left. So that's fine. To do the moment at C, what you normally do, not 100% of the time, but most of the time, is you calculate summation of moments at point C. And that will give you the value of the moment at C. Summation of moment at C, we'll say clockwise is positive. They have to add to 0. And we've got let's see, I'll kind of highlight them as I go, because there's two that are 210 pounds. This 210 pounds has a moment arm of, I think it was called H. No, it's not. Let's see. Oh, wow. They don't just give us this one, do they? So we have to read the problem statement some more. Let's see. There's going to be a key in here. Oh, the key is the triangles here. So I don't have all of the pieces, but I want this height. I want that height right there. That's the moment arm between the horizontal 210 pounds and point C. They don't really give me that. So I'm going to use, let's see. I'm going to use the idea that they've made these two A variables the same. They're both A. So they didn't tell me this height, but I know that it has the same ratio as H to A, but H to 2A. So I'm looking at this triangle. I'm looking at this triangle right here, right? And that triangle has a height of 3 feet and a base of 5 feet. So there's a similar triangle right here. I don't know if you can see that. Yeah, it shows up. This yellow, that little yellow triangle, has a height of what I want to know and a base of 2.5 feet. So it's half of that. So this should be 1.5 feet, right? That's not the actual moment arm I want, though, because I want the moment arm to go all the way up to where the cable is. So they do tell me that it's a 1 foot diameter pulley. So the radius of it right here should be 1/2 of a foot. So it looks like my moment arm from point C up to the horizontal tension in the cable is 2 feet. And it's trying to go clockwise. All right. The other 210 pounds, so this one, is trying to go counterclockwise about point C. There's point C. So I'm going to give it minus 210 pounds times its moment arm. Wait, let's go back to our picture. Is this distance. So I want that distance, which is 4 plus 2.5 plus 1/2, the radius of the pulley. So that's 6.5, 7 feet. Okay. CX and CY are forces that do not create moments about point C, because they're pushing on point C. The moment at C, however, is not a force; it's a moment. So it does create a moment. In fact, remember, it's called a concentrated moment. So it is not a force. It creates a moment about point C, and all you do is, no matter where on the diagram concentrated moments are, when you're writing a moment equation, they just either add or subtract based on what direction you've drawn them. I've drawn this one clockwise. My equation, I decided that clockwise was positive, so it's just plus moment at C. So those three things have to add to 0. If they don't add to 0, it means that the little beam ABC is rotating at point C, and it's not supposed to be doing that. So we have, I don't have a let's see if I can find some calculator that I can use here. All right, clear. So we've got 210 pounds times 2 feet. 420 foot-pounds minus 210 times 7, 1470 foot-pounds. I'm going to move moment at C to the other side of the equal sign, so equals negative moment at C. So 1470, negative 1470 plus 420 is, what does that equal? 1050 foot-pounds, or negative 1050 foot-pounds, equals negative MC. Our negatives can cancel each other out. So the moment at C equals 1050 foot-pounds. The arrow, or well, the sign that we calculated is correct. So it is a clockwise moment at C. Let's see if they want us to plug that into here anywhere. Oh, they do. All right, so no, that's AB. Here's C. All right, so 1050. We had these as both 210. Oh, let's see. Compressive forces with negative number. Ooh. These reactions aren't really tension or compression, so I don't know if they want positive or negative signs on these or not. Let's see. Doesn't like any of them. 525, 105. Oh, did I not? Oh no. Did I not divide? I didn't divide by 2 up here. Look at that. I even wrote it down, but I didn't divide by 2. So 210 over 2 is 105 pounds. So what that changes is all of these. Probably some of y'all were writing that down and saying eventually you'll figure it out. And so these 210s become 105s. And that becomes 210. This becomes 735. This becomes 525. All right. And it did want some negative signs on there. That's, that's a bit tough to figure out what direction they want these, because it was arbitrary which direction we assigned the arrows. So it's sometimes where it gets a little, oh, it wants a negative on that because, let's see, it probably does say something about that. Counterclockwise moments with positive. We did say that this was a clockwise moment, so that one's easy to figure out, that it should be negative. All right. We even show a clockwise moment. When you write these concentrated moments, 525 foot-pounds, usually it's better off that you go in and write either clockwise or you write it as 525 foot-pounds, and then you actually draw a clockwise arrow, or counterclockwise if it's counterclockwise. Because plus and minus they only mean something in the context of whatever you decided when you wrote that equation. So it's better, just like when you do tension and compression and you write a T or a C, then it's best to either write CW or draw the arrow when you're talking about a concentrated moment. All right. Let's see. So we've done like one piece of one step. This is normally the first step when you're, the first step if you're doing frames and machines. Let's kind of write out what our steps should be. And again, these are not 100%. There are always, it always pays to spend 30-something seconds looking at the picture, trying to figure out what way you're going to approach the problem, because there could be a better way than what we're going to write here. But typically, first thing, let's draw the free body diagram. And that's almost always going to be the best answer for an engineering problem, is to draw the diagram, whether it's a control volume or a free body diagram or a circuit diagram or whatever it is. That's usually the best thing to do. Two, I guess at some point you have decided that this is a frame or a machine and not a truss, so I'm not going to write that down. Two is, assuming this is a frame or a machine, it probably pays to look for two force members. We didn't do that. So let's go look at ours and see if there's any two force members in it. So when we look for two force members, we really only have three members here. We have ABC, ADE, and BE. The cable is technically a two force member, but it's different. It's not a rigid member like these others. So technically it would be two force also though. So we're looking for any of these pieces that follow the truss rules. So they have only two pins, no external force applied to the body of the member, only forces are at the pins. So ABC has two pins and the fixed support, so it's definitely not a two force member. ADE has three pins. One of them's connected to a roller, but it's still a pin that's applying force there. So that's not a two force member. BE, two pins. It's got two letters, B and E. There's two pins there. And there's no force applied to member BE, no external force. Only forces are at B and at E, the pins. So BE actually is a two force member. So how am I going to mark that down? We'll just do this. BE equals a two force member. Yeah, it's just messing me up. I don't know why it wants to not work the way I want it to. So that's useful, particularly since they talk about one of the things we want to do is the change in length of member BE. So that means we have to figure out the force in BE, and it's going to be a two force member. All right. So now we've got a little free body diagram here. A, B, C. That's D and E. What we want to do is, we've looked for two force members. The next step is typically, but not always, solve for external reactions. If you've decided this is a machine and not a frame, then a lot of times you have to skip this step. So you may have to skip if machine. And you'll know because there won't be any way to solve for the external reactions. Or that's what the problem is even asking you to do. That problem is asking you to solve for these external reactions, or they're already given. So if it's a machine, you may skip the external reaction solving. But ours was a frame, so we did find our external reactions. Next, the next thing you do is, so in a truss, you kind of do these same things. You draw the free body diagram, you look for zero force members, you solve for the reactions, and then you either do method of joints or method of sections. So here, we can't do method of joints or sections because we don't have a truss. So what we do is we I'm going to write a very general statement, and then you'll have to figure out, exactly how to apply that in every instance. But I'm going to write, draw free body diagrams of members of interest is what we'll do. So like in our problem statement, it says we would have to determine all forces and moments acting on member ABC. So member ABC is a member of interest. Change in length of member BE. So member BE is a member of interest. And so what you do is you act like you're unbolting or unpinning that member from the frame or machine, and you draw just that member. So I'll kind of write that: unpin from frame and draw just that member. The free body diagram of just that member. So in our case, the first thing it asked about was member ABC, the bottom piece here. So I would take member ABC. We'll leave room for a step 5 in there, so we'll drop down a little bit. So there's A, B is somewhere over here, and C is over here. C is not really a pin, it's the fixed support. I'm just drawing a dot to represent point C. And ABC is not a 2-force member, so I can't just put the 2 arrows on the end of it. Point A was connected to member ADE, that kind of diagonal one. It's just a pin, so I just have to put AX and AY. B is connected to member BE. Member BE is a 2-force member, so at B, instead of writing BX and BY, I can just write the force in member BE. I don't know if it's up or down, but I know it's in this line of action. So member BE is a 2-force member, so if I take and connect the dots between E and B, that's the line of action for the 2-force member. So I don't know, if it's pointing upwards or downwards, so I have to pick one. But I do know it's on that line. All right. C, we already solved for. So I go over here and find, well, C, the moment is 525 foot-pounds clockwise. So I draw a clockwise arrow and 525 foot-pounds. CY, 105 pounds going up. CX, 105 pounds going to the left. I have that negative sign, and I drew CX going to the right, so that means the negative sign means it's really going the other way. So it's like that. And so a lot of times when you get to this member of interest, you've drawn its free body diagram, then apply equilibrium equations which I'm talking about summation. Whoa, wow, that's really scratchy. Summation of forces in X, summation of forces in Y, and summation of moments. So apply those equilibrium equations to the free body diagrams that you just drew from the members of interest. So like this free body diagram we just drew. Now we didn't finish it because we didn't put our dimensions on here. So from A to B, looks like it's 5 feet. And from B to C, I'm pretty sure it was 4 feet. We'll check that in a second. And technically, you know, somewhere we need to put a x-axis and a y-axis. I usually don't worry with drawing those, but they are part of it. that down there. Okay. Unselect. All right. So at this point, you may or may not be able to apply all of those equilibrium equations. In this case, we actually can. There's three unknowns, AX, AY, and the force in BE, and I have three equations, so I should be able to solve for all of these. If I had not known, if I went back up here and I did not know or recognize, whoops, that's not what I wanted to do. I wanted to not do that. I wanted to do this. Had I not known that BE was a two-force member, when I got to drawing FBE, if I didn't know it was a two-force member, I would have had to draw BX and BY. I would have four unknowns and three equations. I couldn't have solved for all of them. So it is important to be able to find all of the two-force members sometimes. If you ever get in a situation where you've got too many unknowns and you've drawn all your free body diagrams that you could, then you probably missed a two-force member somewhere along the way. And that's going to eliminate a bunch of your unknowns once you find it. But we didn't miss it, so we do have this equation, or these sets of equations that we can go in and we can solve for all of these variables. Let's do the easiest one first. To me, the easiest one is AX. So it says that AX is going to the right, minus 105 pounds over there at C equals 0. So therefore, AX equals 105 pounds. Correct sign orientation, so it's going to the right. So we got that one. If I write the Y equation, I end up with two unknowns in the Y direction, so that's not going to be as useful to me. If I write the moment equation in the right place, I can solve for one of those. So let's write summation of moments equals 0. We'll do clockwise positive. And we need to pick a location that will eliminate one of the unknowns. So we either need to sum moments at point A or at point B. Because if I sum moments at point A, then I will not have AY in this equation. And if I sum moments at point B, I will not have FBE in this equation. If I sum moments at point C, then both of those two equations, two unknowns, AY and BE, would be in the equation, and I just end up with having to do simultaneous equations or something like that. So I'm going to say, let's do the summation moments about A. Why not? So that will be the way I drew it. I said clockwise is positive. The way I drew BE is negative counterclockwise. So FBE times 5 feet. Oh, I said I was going to check that moment arm of 4 feet. Let's check it. Yes, it is 4 feet up there. All right. Minus 105. This is the 105 on the far right at C, the vertical one. It has a 9-foot moment arm. The 105 horizontal has a line of action that actually goes through point A. So it does not create a moment about point A. The 525 though, it is clockwise. It's a concentrated moment. It already has feet in the units, right? Foot-pounds. So I don't need to multiply by a moment arm. I just need to add or subtract. So it's going clockwise. I said clockwise is positive. So plus 525 foot-pounds. All of that has to add to 0, or else the little beam at the bottom is rotating about point A. So it's not doing that, so I need to make sure that it balances out to 0. All right, let's get our calculator out and see what we have. All right, I've got I'm going to move FBE times 5 feet over to the left side. So I've got FBE positive times 5 feet equals negative 105 times 9, 945, negative, foot-pounds, plus the 525 from the concentrated moment. So 945, well, negative 945 plus 525 is 420, negative 420 foot-pounds. I still have to divide by that 5 feet though, so therefore the force in member BE equals 420 divided by 5, 84, and it's negative 84 pounds. The feet get divided out. So that means that FBE should be pointing down on this piece. That can get confusing also. I gave a little spot here to draw the free body diagram of BE. So once you've already established some directions here, like I chose directions for AX, AY, and BE as soon as I drew this free body diagram, that kind of sets them for the whole system. So if I go and draw BE, I have to keep following this same convention that I set. So I said that force in BE points away from the body. So that means at E, it has to point away from the body. And at B, it has to point away from the body. Same magnitude on all of those, but that's the sign convention. Now, I solved for it, and it turns out I was wrong. It's supposed to be negative 84. So that means that BE should have 84 pounds of compressive force, shortening it up in it. And that will go into this change in length in member BE, part C. We haven't even finished part A yet, though. All forces and moments acting on member ABC. We've got the force on BE. We have AX. We don't have AY. So now we could go in and we could do two things. We could do summation of forces in the Y direction, which is what I am going to do. Or we could write another moment equation and do moments about BE or C. Either one. I'm just going to do Y. So that one says AY. I'm looking at my free body diagram. It says plus FBE, according to the diagram, plus 105 pounds equals 0. Then when I plug in BE, I get 0 equals AY minus 84 pounds, because FBE is actually a negative 84 pounds, plus 105 pounds. So negative AY equals 105 minus 84, 21. So therefore AY is a negative, meaning I chose the wrong direction. It should be going down 21 pounds. Just checking this out, make sure that's right. That looks right. All right. So now we could start trying to plug some of these into web work and see, whoops, where is he in there? See if we got anything right. So let's see. The reaction at A in the X direction, and well, we'll have to figure out if, I assume that that's going to be our AX was 105 pounds going to the right. So we'll give it 105. AY, I think it's going to be the negative 21. BX is, it's labeled as BX and BY, but we know that B is just a Y, so BX is actually 0. Y is that compressive force, negative 84. And let's see if we got those right. Look at that, all that green. Good. All right, so now we have these last two parts. So the last two parts are the shear, so they're more the mechanics of material stuff. They're not really frames of machines, static. Frames of machines are a static topic. And what we're doing now for part B and C, these are mechanics of materials, how to knowing the forces on stuff, how do they respond? Do they stretch? Do they break? Yield, all this kind of stuff. So part B here is the shearing stress on the cross section of the 1/2 inch diameter pin at D, which is in double shear. All right. We don't have a D on this diagram. We do have one here. So the force on D, when you have a frictionless pulley, why don't we redraw just D? So here's our pulley at D. So we've got this, it was 105, not 210. I need to change that on that top one, don't I? Yeah, we wrote it. I just realized that because we didn't divide by 2. There we go. In case anybody ever looks at this thing again, they won't wonder where that 210 came from. So 105 and 105 pounds here. As long as this pulley is frictionless, then if it's convenient to you, you can take point D and put those cable forces right at point D. So that could have actually been a little bit convenient for us earlier, right? When we were doing these, trying to figure out these moment arms, and we were having to add half the diameter of the pulley, these 1/2 feet here and there. Maybe that would have been useful to just put the tension right at point B, and it would have saved us a little bit of effort. But here it certainly will help us, because what we want to know is what's the resultant force on the pin at D. So resultant, well, that's not resultant, resultant at D. In this case, they're both 105 pounds because they're both the cable forces. Let's see what that equals. Let's see. Oh, it didn't. Oh, that's silly. I think it's... No, that's not it. This is calculators on my phone, and it's acting kind of strange. I can't find the... Hmm. 148.49, I think. 492 pounds. All right. So it's just the, square both of the components. These components are at right angles to one another, so I don't even have to worry about it. Now, if they were at different angles, I'd have to get their X components and their Y components and figure out the actual resultant. Since these are perpendicular to one another, it makes it a lot simpler. All right, so 148.492. And it gave us this little clue up here that the pin has a 1/2 inch diameter. So pin at D equals 0.5 inch diameter, and we want to know the shear stress. Tau equals the shear force V over the area. It said it was in double shear, so the shear force is 148.492 pounds, and the area is 2 times pi, the diameter of 1/2 inch, pi d squared over 4. This calculator is probably going to have a lot of trouble solving this. I have MathCAD open. Why don't we just drop it into MathCAD and do it there. All right, let's just put this guy in here. So 148.492. These need to be pound force and math. Oh wow, we got caps lock on. Pound force over 2 times pi times 0.5 inches, all of that squared, over 4. I don't know what units it wants. Let's see. It wants PSI. So let's go turn that into PSI. 378.132. Let's see if it likes that. Yes, it liked that. We're all but one thing left. So that was the double shear on the pin at D in the center of that roller, or not roller, pulley. The last thing they want is the change in length of member BE, so this vertical piece, which we decided was a 2/4 member, if it has a 0.2 inch by 1.1 inch rectangular cross section, and it gives us the modulus of elasticity. So, oh wait, that's MathCAD. So it wants delta of member BE equals the force in member BE times the length of member BE over the cross-sectional area times its modulus of elasticity. So the force was negative 84 pounds. So the negative means it's compression. The length, I don't remember. It was H. 3 feet. So from in, and notice, you know, there's this little piece sticking up here that's above E. We don't need to know the height of that. For one thing, that part wouldn't get squished. You know, if the forces are actually at B and E, then that little tab sticking up there is not going to change length. It might drop down, but only by the amount of compression between B and E. So we don't have to worry about that little tab. So it's just 3 feet is the length between the pins. Now, I want this to come out in inches, so I'm going to convert to inches right here. And then they gave us dimensions for its cross-sectional area being a rectangle. 0.2 by 1.1. So 0.2 inches times 1.1 inch. That's its area. That's a 0. And then they gave us the modulus of elasticity as 30,000 KSI, I think it was. Yes, so that's 30 million PSI. And now we just need to do this math. Again, my little calculator over here is not going to do well with that, so we'll put this in MathCAD also. And we'll make it a little smaller so it's not gigantic. All right, so negative 84 pounds times 3 feet. I don't have to worry about the conversion factor. MathCAD will convert for me. Divided by 0.2 inches times 1.1 inch. That's the area. Oops. Times modulus of elasticity, 30 times, well, I can just do PSI, like that. And I want it in inches, I'm sure. Negative, because it's getting compressed, 0.4582 times 10 to the negative fourth. So 3 zeros and a 4. Negative 0.1234582. That's really small, but let's see. It is correct. It's only 84 pounds in a 1 inch thick. This is a solid piece of 30 million PSI is the modulus of elasticity for steels. So this is a 1 inch thick piece of steel with 84 pounds on it. So it's not going to change length a lot with only 84 pounds. And sure enough, it's, 4/10,000 or 5/10,000ths of an inch that it compressed. All right. I think that gets us several different pieces of how to deal with frames of machines. We're going to keep working with frames of machines. I don't know that we need to do another one just today until y'all have practiced a little bit. So what I'm going to say is homework, all the homework from the first part of the exam, first part of the quarter is still open for another 3 days. So if you've got stuff from old web work, even though it's not like we're about to take exam 1, finish that stuff up so that you get credit for it. Web work, the homework is, I don't know, it's like 10% of the grade or something. So don't just let it sit there. Go ahead and finish that. But as soon as you're finished with that, do 1 or 2 of the frames and machine problems from homework. I think it's 9 or 8. No, it's 9. Homework 9. Do a couple of these. That one doesn't look like a frame or machine, but it is. It's a really simple machine-ish frame, I guess. That one there's one that's pretty obvious. That's actually a good one to start with because it's not too many pieces, and you can and it's got a thing you need to recognize, 2 force member. So do that, and then we'll come back on Wednesday. Hopefully you've had some questions that you can ask that I can work through, and we can go through and look at some more frames and machines. And when we get through with that part, we will begin this topic that is related to frames and machines, and it's that these pieces, no, not those pieces. Where are they at? These pieces like this, we've just been calling them members. When they're not 2 force members, they're going to be called beams. And we're going to have some special things that we can do with beams. We're going to be able to talk about beams deflecting. They're warping out of shape. They're going to go flex up or flex down. We're going to be able to figure out how much they deflect. So there's a lot of stuff that builds on top of these frames and machines. And it's the topic of beams. So try out 1 or 2 of the frame problems. We'll work some more on Wednesday, and we'll introduce the idea of beams. Also, if you want to see more problems worked out, like frames and machines, probably a little bit slower than what I did here, then you've got this intro thing, and it's a different problem that I worked there. It's got a lot of the same type of pieces in it, but actually that's probably a more complicated problem to work out. And there's a whole other set here that if you want to see another example worked out. But that's going to be our intro to frames and machines. I'll see you back on Wednesday. Let me know what questions you have. Looking at our poll here, it looks like it wasn't really bad. 6 people answered the poll, so there's not that many points of data. The average so far is slightly below 70, like 68 or something, which it'll go up by the time I finish doing my part of the grading. So I anticipate exam 1's average to be about average, 70 something. And so that's not bad. That's good. Exam 1 is typically the lowest grade of the 3. I don't know if it's necessarily the hardest one, but it's the first one, and this is a new type of topic that you might not have done before, so it's typically the lower of the 3 grades. All right, I will see y'all Wednesday.